Hello, in this video we are going to see how we can design and simulate a microstrip rectangular patch antenna with coaxial prop feed. In case of a microstrip patch antenna, it consists of a radiating patch which is backed by the ground plane. And these patch and the ground plane are separated by the dielectric. Here this green one is the dielectric and this is the radiating patch and this is the ground plane. And here you can see that this is the connector which is connecting this antenna to the external devices. So this is the an example of a connector. This is an SMA connector. Here you can see that it has an inner conductor and a dielectric and an outer conductor. So inner conductor and outer conductor are separated by the dielectric. So if you connect these connector to the antenna, this inner conductor is connected to the radiating patch and this outer conductor is connected to the ground plane. So in case of the coaxial feed, the inner conductor is attached to the radiating patch and outer conductor is connected to the ground plane. This is how this coaxial line feeding works, or probe feeding of the patch antenna works. In this case, we can see that it is very easy to fabricate and match, or in other like edge feeding, we have to design these feed lines and we have to make sure that the width of this patch is matching to the 50 ohm. But in this case of probe feed, it is very easy to match and it has low spurious radiation. This means that in case of a edge feed patch antenna, there may be lots of radiation happening from these feeds. Like if you are going to feed from this position, some part of the radiations will be happening extending from this feed position. So if there are any other components near to this in a PCB line, it will cause the interference. But in this case, as it is connected directly to the patch, it, it will cause less spurious radiation. That is one of the advantages of this coaxial feeding. And one other property is it is narrowband, similar to other feeding cases also. And one other thing that we have to consider is, because as this feeding has to be go through this dielectric material, if the thickness of the dielectric is very high, it is not easy to model these type of feeding. So this is the design designed values for a patch antenna. All these values like length and width can be calculated using the design equations. So we have a video in our channel describing how this length and width can be calculated. Otherwise, we can calculate this length and width using the online calculator. So here our aim is to design a microstrip patch antenna with probe feeding at 2.4 gigahertz, and we have to use a substrate FR4 having thickness of 1.6 mm. So here we have to decide the position of the probe feeding. So this is a general concept, like if the distance of separation of the probe from this center point. So this is the center point of the rectangular patch. So if it is at a distance of L by 4 from this position, this will provide as a point where the impedance is 50 ohm. So sometimes we may have to move this point a little bit to get the proper matching. So this is just a rule of thumb. Otherwise, if we need the correct information, one thing we can do to get this feed position is we can find out the impedance at this point and we can use these equations like r in y equal to 0 cos square pi l by 0 and find out where this matching of 50 ohm happens. So this is one of the case where how we can decide the probe position. Otherwise, we can simply use this positioning like it has to be extended at L by 4 from the center of the patch antenna. So let's see how we can design it using the CST. So I will show you how we can calculate the length and width using the online calculator also. Let's see that. So this is the online tool from the Pasternak. Here you can provide the dielectric constant and dielectric height and the operating frequency. If you click on calculate, you will get the width and length corresponding to the patch. So this is one of the method that you can decide the length and width. Otherwise, you can always use the equations. Okay, let's start the simulation. Antennas, planar, time domain. I'm going to select the frequency as 4.8 so that the mid frequency will be 2.4. Okay, so let's modeling. Oh, sorry. So first of all, I have to draw the dielectric. So I'm going to draw the dielectric, and here we have to define the dielectric width. So I'm going to use the parameter dw for that, and length I'm going to use the parameter dl, and zmin it is from 0 to h, it is 1.6 mm, and the material is FR4. So let's go for FR4 low C. Low. So when click OK, it will ask for the dw. So this dw is the dielectric width along the width axis. So in our case, our patch width is around 40. So I'm going to give the dimension of the dielectric as 60, and dl it is, I'm going to give it as 50. H is 1.6 mm. So we have the dielectric. Now our next step is to draw the ground. So I am going to use the same dimension as that of the dielectric here. As it is ground, I'm not going to give any thickness, and the material is PEC. So it created the ground plane. And my next step is to draw the patch. Again, go to modeling. So this is my patch. So we have already designed the patch dimension. I'm going to use the values L here. Oh, sorry, minus L by 2. And as it is on the top of the patch, I'm going to use H plus 0.035. I'm going to provide some thickness here. So W that we have calculated as 38.37, and length is 29.76. Okay, so now we have the patch. So our next step is to use the probe. So here you can see that how the probe has to be used here. So it has to be at the center along the width axis, and along the length axis it should be L by 4 from the mid. And in a connector, when you consider the connector, it has an inner conductor, dielectric, and outer conductor. So previously I had done a simulation to decide what should be the inner conductor dimension, dielectric dimension, and the outer conductor dimension. So I have uploaded the same video in our channel. If you are interested, you can look that. So the R1 is the radius of the inner conductor, it is 0.45, and R2 is the radius of this dielectric, that is Teflon, it is 1.5, and R3 is the radius of this outer conductor. So there I have simulated and checked the S parameters, and I had make sure that it is working properly. Here you can see that S11 is very low and S21 is very high. That means that it is transmitting without any loss. And here also you can see that impedance is around 50 ohm. So these values I am going to use while designing the probe here. So first of all, I have to use the inner. So I'm going to use inner, and inner radius, it has to start from R0 to R1, and x center is x is along this direction. So along this direction we know that it has to at the midpoint, that is at 0, and y is, it is from 0 to L by 4. So I'm going to give as minus L by 4. Z minimum, I'm going to give it as h min, some parameter, and it has to be up to top of the patch. That is, it has to be up to h plus 0.035. So here R1 is 0.45. H minimum I'm going to give as minus 6. So here you can see that I have the inner conductor which is connecting from below to here. So it is happened from L by 4 from the center. So click OK. Next thing is I have to design, because in this conductor we know that it has inner conductor, dielectric and outer conductor. So my next aim is to design these things. So the outer conductor has to be get connected to the ground plane. So here you can see that now the inner conductor is in contact with the ground plane. So we have to remove some portions from the ground so that this connection can be avoided. So next I am going to draw a circle to subtract from the ground plane. So its radius has to be from 0 to outer radius, that is the radius of the outer conductor R3, and for this also x center 0 and y center minus L by 4 has to be there, and Z minimum as it is on the ground plane, Z min and Z min you can give as 0 and PEC. Then click OK. R3 is 1.8. So now we have this circle. So now I'm going to subtract this ground and this portion. So now you can see that the inner conductor is not in touch with the ground plane. So my next aim is to draw the PTFE material. Its radius is from R1 to R2. X center is from 0 minus L by 2. And Z min is from H min to 0. It has to from this position to this ground plane, and its material properties PTFE. So we can search for PTFE lossy. So R2 is 1.5. Oh, why it is there? I may have to check PTFE. So X and this is minus L by 4. That was the mistake. So we have the PTFE here now. So while designing the PTFE, make sure that this X center and Y center are 0 and minus L by 4. So we have that probe there. Our next thing is to provide the ground plane so that it can be extended from here to here. So this is the outer conductor, and its inner radius is from R2 to R3. X center 0, Y center minus L by 4. Z minimum is from H min to 0, this position. And this material is PEC. So now we have that one. Okay. Okay. So to make sure that it is getting connected, I am just going to increase. Okay. I have to make sure that the outer conductor is getting connected everywhere. Okay, so the R3 is the dimension. I'm just going to increase that to 1.9 to make sure that it is completely connected to the ground plane. So here you can see that it is getting connected. So while using the coaxial probe, you have to make sure about the this dimension and the R2 dimension. So now we have the patch, and now next step is to use the probe. So use the letter F, which will help us to select the face. So if you click on this position, it will select this face, and if you go here, port, new waveguide port, it will be creating the new waveguide port, and you can just click OK. So we have the port now, and we can do the simulation. So before that, make sure that the background is normal and the boundaries is lambda by 4. Then you can start the simulation. You can start the simulation. Okay, simulation is complete. You can check the S parameter here. You can see that we have the resonance at 2.29 gigahertz. So if you want to modify the resonant frequency, what you can do is you can optimize these parameters. Like you can go for the simulations and you can use the parametric sweep and go for new sequence, and the parameter you have to use because you have to optimize the length. So you can, because if you have to increase the frequency, you have to decrease the dimension. So maybe you can go to maybe 28 something, and using some number of samples, if you start the simulations, you can get some optimized values for the resonant frequency at 2.4 gigahertz. Here I'm not going to do that. We can check the fields. Okay, so the resonant frequency is 2.29. I'm going to create some field monitors for 2.29. So we have all these things, and then again, if you do the simulations, you will be having all that values. Okay, the simulation is complete. Let's check the electric field. Okay, so if you want to check the electric field on the patch, you can go for the field on plane, cutting plane, and as the above patch is on 0.635 mm, you can give this value here. If you want to check the field on the ground, you can put 0, and if you want to check the top of the patch, you can give 1.635. So here you can see that electric field is maximum at the ends and minimum at the center. And if you go for the surface current, you can see that the surface current is maximum at the center and minimum at the ends, as it is the open circuits at both the ends. And far field, here you can see that this is the far field, and the value of the directivity is around, maybe we can, sorry, not far field, transparent. So here you can see that it has a directivity of 6.36. As our aim is to find the gain, you can click on the gain. Here you can see that gain of the antenna is 2.95. That means that the efficiency of the antenna is very less, because as we are using the lossy dielectric, there will be a lots of loss happening inside the dielectric. So if you have to improve the gain, one thing you can do is you can change the dielectric to any lossless dielectric materials. Okay, so if you go for the electric field, you can see that the electric field, okay, maybe we can use the arrows to show. So my purpose now is to see the fringing field. So I'm going to use the cutting plane. Why? Not why. Okay. So let's see how the fringing field is there. I'm just going to use the cutting plane. Is that maybe okay? So this is okay. So we are using the cutting plane. If you use the animate field using the contours, you will be able to see. Sorry, cutting plane. Not is it? Okay, here. Okay. So now it is clear. So now you can see that how the electric field variation is happening at the ends, and maybe if you use the arrows, oh, the arrows is not clear. So it may be best to use the contours itself and click animate. You can see that how the field distribution is happening and how the fringing is happening at the ends. I hope you get some idea about how to design a patch antenna using the prop feed and how to decide the prop position. Okay, maybe we can check the impedance. Also here you can see that 2.29, our resonance frequency is 2.29, and if you click on real and imaginary, you can see that the resonance frequency is around 50 ohm here. So that means that it is good matching. Here you can see that the values, sorry, here this is the value, it's around 47. So that means that it is good matching for our case. I hope you get some idea about how we can design a patch antenna using the prop fed. Thank you.